Hello physics students, welcome to the next exciting episode of Gravity. In this episode we'll be looking at satellites. Alright, before we get started, I usually ask this question: how many ways do you think physics students can spell satellites? You wouldn't think there's that many. What do you think? Greater than 20? 11? I asked this because one year at the end of year paper I was marking a question that dealt with satellites, and it was one where they had to do a calculation, but they also had to talk about satellites and the physics related to them. And after a few papers I was just amazed at the variety of ways that students could spell satellites, given that the word was correctly spelt in the question, and yet students still spelled it incorrectly. Anyway, have your guess. Where do you think? Commit now. I found 24 different ways to spell the word satellite. So let this be a warning to you. Make sure you spell satellites correctly. Now, you probably all know what a satellite is. It's something that goes around the Earth, various altitudes, but we also send them out into space. We orbit them around the Moon, around Mars, around other planets. They come in all shapes and sizes, so there's a great spectrum of them, but the key factor to them is that they orbit around an object, and the force providing the centripetal force is gravity. Okay, and we'll look at that in a little bit more detail later in a worked example. Just included this photograph to show you the size of some of them are quite big. This isn't too big. This is just pretty standard size. Notice all the gold foil. This is to absorb the charged particles that come from the solar wind, and to dissipate the charge within them so the charge doesn't get into the electronics and things. All that's nice, beautiful gold foil, worth a bit of money. And an ultra clean lab, and in this one I think they're in the final testing chamber, which can be raised to very high temperatures and very low temperatures, and it can also make it to the vacuum equivalent to space, or nearly equivalent to space, and it shakes it and does all the things, because you don't want to put a satellite into space and have it fail. A couple of years ago you could go up and fix them using the space shuttle, but we can't do that anymore, and so if it doesn't work when it's launched, that's a lot of money that's been wasted. Right, so satellites go around in a circle. Make sure you remember your circular motion. We have our formulas there. We have our formulas that relate to the circle and the period of the circle and our centripetal force, and we could use this equation here which combines them. And so with those and our Newton's law of universal gravitation, we can describe satellite motion. So let's have a go at an example. This is a pretty standard question. Here we have a satellite, and because we're learning, let's circle some stuff. So there's a mass, there's a number, there's a number. Let's make that finer. So that would be our mass. This is important because this could be r, but we'll put a question mark next to that, and this is our velocity. Now the question mark about the radius is, it says altitude, and so the altitude is the distance above the surface, but when we're talking about circular motion we go from the center of the circle, which must be the center of the Earth, so we must include the radius of the Earth as well. Alright, let's get rid of those. So they put it in. The first step is to work out the orbital radius, and although you're not given it here, you'd be given it elsewhere. The radius of the Earth is approximately, different books use different numbers, 6,380 kilometers. Convert that to meters and we have its radius, and then we put it into the centripetal force formula, mv squared on r, and we get 6,900 newtons, and that's using the centripetal force. So that would be, let's get this going again. Alright, so if we have our Earth and we have our little satellite with its solar panels, sort of, that's our very dodgy. What we're saying there is the centripetal force towards the center of the circle is this value here, as it goes around maintaining a constant radius. relative to the center of the circle. Now we could have also calculated this using, or this force, because we would recognize that for satellite motion, let's get a better color, let's erase that. Oh, you idiot. Let's erase that. Let's get back. What was I using? Let's do nice and big. For satellites, the centripetal force is provided by the force due to gravity. Nothing else is holding on to them, and so we could have calculated this using G m1 m2 on r squared, where the first mass would be the mass of the satellite, the second mass is the mass of Earth. This is the radius of the orbit, remembering this value over here, and we could work it out, and the two would be the same. And fortunately, if I get rid of all this and I move on, they've done the calculation for us using this equation here and got the same value. Isn't it good? So it's true. Notice they're setting out. I like this setting out where they've got all their numbers in brackets. They'd be using their EXP button to raise things to the power, and they haven't forgotten the square. So that's good working out. I like that. Now, how do you launch a satellite? Quick little question is basically sometimes you're asked how they get the satellites up into space, and you need to remember that a couple of things. They launch them to take advantage of the Earth's rotation, so most satellite launches occur close or near on the equator, and because the Earth is spinning, they're using the Earth's velocity to help the satellite get up into space. Now there's also another question which is relates to what's called Newton's cradle, or not Newton's cradle, that's the balls that knock together, Newton's cannon. And what Newton proposed was if you had a cannon on the surface of the Earth, and that cannon was able to fire a projectile, and you ignored air resistance of course, and you could increase that velocity that the projectile came out, what would eventually happen is, if that's the curvature and you have your cannon, okay, with a low velocity the cannonball falls to the surface. With a greater velocity it would fall further, it would travel further whilst experiencing gravity and falling due to the influence of gravity. But if you fired it with enough velocity, its rate of falling towards the Earth would be the same as the curvature of the Earth, and therefore it would go around in a circle and continue on. And that's the basic principle of satellite motion. If you can put a satellite into an altitude and give it enough velocity so that it goes round in a circle, it's continually falling towards the Earth, if we're using Earth as an example. However, the curvature of its falling is the same as the curvature of the circle around the Earth. Obviously, if you fire it too quickly, the satellite will escape and gravity cannot pull it back. So it's a very fine balance between gravity and the centripetal force. And why I have that there is on our OneNote, and there's a couple of links to some animations or some web pages where you can play with Newton's cannon and explore that concept. And this is basically the principle of it. Okay, so much better diagram than mine. In the next video we're going to look at Kepler's laws. We'll continue looking at satellites, but we'll also look at Kepler's law. Cheerio!